This is AP Calculus Practice Exam 1. In Part 5, we will finish up the multiple choice section that is calculator active. If you have not seen Parts 1 through 4 yet, either click the link in the upper right-hand corner or find the link in the description. The graph above gives the velocity v in feet per second of a car on the interval from 0 to 8, where t is the time in seconds. Of the following, which is the best estimate of the distance traveled by the car from t equals 0 until the car comes to a complete stop? We have memorized into our bones that the integral of a rate from a to b is equal to the change in amount from a to b. More formally, we can write the integral of f prime from a to b is equal to f at b minus f at a. This is the first fundamental theorem of calculus. Can you see how this is still saying the integral of a rate is equal to the change in the amount? Notice that we go from f prime to f, where f is just the antiderivative of f prime. The antiderivative of velocity is position. So the integral of velocity from a to b will equal the position at b minus the position at a. So just like we might say that the integral of a rate from a to b is equal to the change in the amount from a to b, the integral of velocity from a to b is equal to the change in position from a to b. In the context of this problem, the integral of velocity from 0 to 8 will be the distance traveled by the car in feet from time t equals 0 seconds to t equals 8 seconds. That is exactly what we are being asked to estimate. So if we can estimate the integral of velocity from 0 to 8, then we will have estimated the distance traveled by the car. They gave us a graph of the velocity of the car from 0 to 8. So to estimate the integral of velocity, we need to estimate the area under this curve. So how do we do that? Let's start by estimating the number of squares that are below the curve. I have highlighted the squares that are completely below the curve, and if you count them up, you'll find that there are 15 of those. So now we need to estimate sort of partial squares, so we can add that number on to 15. A quick way of estimating the remaining number of squares below the curve is to count the squares that are at least 50% below the curve. Of course, each of the squares we are counting have some extra square that's above the curve, but this will be somewhat canceled out by the fact that there are pieces of squares below the curve which we are not counting at all. No, this is not very precise, but it is okay because we are just looking for the best estimate. Anyway, there are about 6 additional squares under the curve, for a total of 21 squares. Notice that each square has an area of 10 feet. That's 1 second times 10 feet per second. So the total area under the curve is approximately 21 times 10 feet, or 210 feet. So the answer is D. For the interval from negative 1.5 to 1.5, let f be a function with first derivative given by this expression. Which of the following are all intervals on which the graph of f is concave down? F will be concave down where f prime is decreasing, which means f double prime will be negative. It's this last one that is most useful because if we can come up with an expression for f double prime, we can easily tell where it is positive and negative by either making a sign chart or we can graph it since this is calculator active. F double prime is just the derivative of f prime. The derivative of e to the u is e to the u, so we can start off by writing e to this trinomial, but then the chain rule demands that we multiply by the derivative of the inner function, which will be 4x cubed minus 4x. So this is f double prime. Let's graph that second derivative on the graphing calculator. So hit y equals and go ahead and type it in. If you're wondering why I have typed it in on y3, leaving y1 and y2 blank, it's just something that I do. I always put the original function on y1, I put the first derivative on y2, and the second derivative on y3. That way, when I have more than one function, it's easy for me to remember which one is which. Anyway, we are ultimately going to be looking for the x-intercepts, so most students find it easier to go ahead and graph an equation for the x-axis. So that's why I put in the 0. So if we hit zoom 9 to get a standard viewing window, we have this. However, in the setup of the problem, we are told that the function is only defined between negative 1.5 and positive 1.5. So let us adjust the window. So x min will be negative 1.5 and x max will be positive 1.5. Let's hit graph again and see what we've got. Remember, we are looking for the intervals where f double prime is negative. So we see that f double prime is below the x-axis from here to here and from here to here. So this second piece is from 0 to 1. But what about this first piece? It's something to negative 1, but should I say negative infinity? No. Remember, we set the window to match the domain given to us in the setup of the problem. So the window goes from negative 1.5 to positive 1.5. So the left edge of this graph is negative 1.5. So we're going to say that f double prime is negative on the interval from negative 1.5 to negative 1 and from 0 to 1. So the answer is D. The graph of f prime, the derivative of f, is shown in the figure above. The function f has a local maximum at x equals which of these? F has a local maximum when f prime changes from positive to negative, because that means that the original function f went from increasing to decreasing. At negative 3, f prime goes from negative to positive. It goes from being below the x-axis to above the x-axis. This would be the location of a local minimum. But at positive 1, f prime goes from positive to negative. It goes from above the x-axis to below. This indicates the location of a local maximum. So the answer is C. If f prime of x is positive for all real numbers x, and the integral of f from 4 to 7 is equal to 0, which of the following could be a table of values for the function f? If f prime is always positive, then f is always increasing. Right at the beginning, we are told that f prime of x is greater than 0 for all real numbers. That means that f of x is always increasing. Let's see if we can eliminate any of the choices based on that alone. Negative 4, negative 3, 0. That's increasing. Negative 4, negative 2, 5. Those are all increasing. Negative 4, 6, 3. 6 to 3, that's decreasing. So we can eliminate option C. 0, 0, 0. That's flat, not increasing. So we can eliminate D. 0, 4, 6, that is increasing. For the remaining tables, let's draw some basic sketches. For example, table A might look something like this. In the setup, we are told that the integral of f from 4 to 7 is equal to 0. Does that match what we see in the graph of A? Well, no, because the integral of f from 4 to 7 would be the area under the curve between 4 and 7. And because this area is below the x-axis, this would be negative. There's no way that this will equal 0, so we can eliminate A as an option. Here is a rough sketch of option B. Is it possible that the integral from 4 to 7 could be 0? It is possible because this integral has a negative area below the x-axis and a positive area above the x-axis. These could cancel each other out and make 0. And here is a rough sketch of option E. Could the integral of this graph be 0? No, this integral could not equal 0 because the area is entirely above the x-axis. It has to be positive. So the answer is B. Did we really need to draw these graphs in order to answer the question? Well, no, we could have just visualized it. Looking at option A, we can tell by the -4, the -3, and the 0 that the graph would be entirely below the x-axis, making a negative area. We can tell that option E, with the 0, the 4, and the 6, would be entirely above the x-axis, giving us a positive area. Only option B, with negative values and positive values, will give us negative area and positive area, allowing it to cancel out and make 0. The graph of f double prime, the second derivative of f, is shown above on the interval from -2 to +4. What are all intervals on which the graph of the function f is concave down? F is concave down where f double prime is negative. We are given the graph of f double prime, and we can see that it is negative below the x-axis here and here. That's from -2 to -1 and from +1 to 3. So the answer is E, and that E must be for easy. A person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which the person's shadow is lengthening? Let's label the picture with numbers and variables. A person is 6 feet high, so there you go. The height of the street light is 15, so there it is. The person is walking away from the base of the street light at a rate of 4 feet per second. So I need a variable representing the distance between the base of the street light and the person. Let's call it x. Now I can record this rate on my inventory of information as dx dt. So dx dt is equal to 4 feet per second. We are being asked to find the rate at which the person's shadow is lengthening. So I need a variable to represent the length of the shadow. Let's call it s. So in other words, we need to find ds dt. The red triangle and the blue triangle are similar triangles. We can use this to find a relationship between s and x. So small over big will equal small over big. Focus on the bottom of the red triangle and the bottom of the blue triangle. The bottom of the red triangle is s, and the bottom of the blue triangle is x plus s. So small over big will be s over x plus s. Now focus on the vertical part of the red and blue triangle. Small over big will be 6 over 15. If you cross multiply here, you get 15s is equal to 6 times x plus s. Now let's do the distributive property. So we will get 15s is equal to 6x plus 6s. Subtracting 6s from both sides, and we get 9s is equal to 6x. Dividing both sides by 9, we get s is equal to 6 over 9x. Ultimately, we need to find ds dt. So let's get that expression by differentiating both sides of the equation with respect to t. So on the left, we get ds dt, and on the right, we get 6/9 dx dt. But we know that dx dt is 4. So we get 6/9 times 4, which equals 2.667. So the answer is B. A particle moves along a line so that its acceleration for t greater than or equal to 0 is given by a of t equals this expression. If the particle's velocity at t equals 0 is 5, what is the velocity of the particle at t equals 3? You know how we always say that the integral of a rate from a to b is equal to the change in amount from a to b? When we talk about position, velocity, and acceleration, we usually don't talk in terms of change in amount. Instead, we say the integral of velocity from a to b equals the change in distance from a to b. Similarly, the integral of acceleration from a to b is equal to the change in velocity from a to b. It makes sense that the end velocity will equal the initial velocity plus the change in velocity. In this case, the end velocity, or the velocity of the particle at t equals 3, will equal the initial velocity, which is 5, the velocity at t equals 0, plus the change in velocity. And we just decided that the change in velocity will be the integral of the acceleration. Since we want the change in velocity from 0 to 3, we need the integral of acceleration from 0 to 3. We can use our graphing calculator to evaluate this expression. Let's start by typing in 5 plus the integral from 0 to 3. We have 5 plus. For the integral, we do math 9, and we are integrating from 0 to 3. Next, we type in the acceleration expression. To get the fraction going, we hit alpha y equals enter. In the numerator, we have t plus 3, so we type x plus 3. In the denominator, we have the square root of t cubed plus 1. Put your dx on the end, and that's it. 11.710. So the answer is E. Let f be a function such that the integral from 6 to 12 of f of 2x dx is equal to 10. Which of the following must be true? Looking at the answer choices, I see that we have all t's instead of x's. You know how we very often do U substitution to integrate? Well, we will do the same thing here, but it's going to be t substitution, but the process is the same. T clearly equals 2x. That means t prime is going to equal 2. Now let's do the substitution. We have to be very careful about the limits of integration, so I'm going to leave those off for a moment. Inside we have f at t, but instead of dx, we will write dt divided by t prime. And right now this still will equal 10. Let's deal with the limits of integration now. This 12 is a value of x. We need to transform this into a value of t. T is 2 times x. So if x is 12, then t is 24. Similarly, this 6 is a value of x. To transform it into a value of t, we need to do 2 times x. So 2 times 6 is 12. So this is the value of t. Normally, we would take this 2 and put it out in the front as a 1/2. None of the answer choices have a 1/2 in the front. So instead, let's multiply both sides of the equation by 2 to get rid of the 2. So we will have equals 20. So the answer is B. Let f be a polynomial function with values of f prime as selected values of x given in the table above. Which of the following must be true on the interval from -2 to 6? Option A. The graph of f is concave up. If f is concave up on this entire interval, then f prime should be increasing on the entire interval. Let's check it out. 3, 1. Right there already not increasing. So A is not the answer. Option B. The graph of f has at least 2 points of inflection. If f has a point of inflection, it changes concavity. That means f prime will change directions, either from increasing to decreasing or from decreasing to increasing. F prime goes from 3 to 1. That's decreasing. And then it goes from 1 to 4. That's increasing. And then it goes from 4 to 7, increasing again. And then it goes from 7 to 5. That's decreasing. We have a point of inflection somewhere between 3 and 4 because f prime goes from decreasing to increasing. And then we have another point of inflection somewhere between 4 and 5 because f prime goes from increasing to decreasing. So yeah, the graph of f has at least 2 points of inflection, so the answer must be B. Let R be the region in the first quadrant bounded below by the graph of y equals x squared and above by the graph of y equals the square root of x. R is the base of a solid whose cross-sections perpendicular to the x-axis are squares. What is the volume of the solid? In the first quadrant, the graph of y equals x squared looks like this. And the graph of y equals the square root of x looks like this. So this yellow area is region R. Let's use our graphing calculator to find the x-coordinate of the point of intersection. So let's type x squared in as y1, and let's type the square root of x in as y2. Hit y equals, and type in both equations. Now hit zoom 6 for a standard viewing window, 10 by 10, but we really are only interested in this tiny bubble of overlap right here. So let's zoom in by choosing Zoom Box. It's very fun. Option 1. Move the pointer to the lower left-hand corner of the area of interest. So I'm going to move a little bit to the left and a little bit down and hit Enter. Now move the pointer to the upper right-hand corner of the area of interest. As you go, it's going to draw a rectangle indicating the area of zoom. Hit Enter. So pretty. We need to find the x value of the intersection point. So let's hit second trace, and option 5 is intersection. So just hit Enter, Enter, Enter nearby. So the intersection point is actually at x equals 1. Picture a strange loaf of bread sitting on top of region R. Finding the volume of this solid is a 3-step process. Step 1 is to find the length of the base of a single slice. Step 2 is to find an expression for the area of a single slice. And then step 3 is to find the volume of the solid. Picking a slice at random, the length of the base of a single slice would be the length of this blue segment. We can write an expression for the length of the base by subtracting the top function minus the bottom function. In this case, the top function, shown here in purple, is the square root of x. And then the bottom function is x squared. So this is an expression for the length of the base of a single slice. Step 2 is to find an expression for the area of a single slice. We are told in the setup that cross-sections perpendicular to the x-axis are squares. Remember, we are picturing a loaf of bread that is sitting on top of this yellow area, and we are looking down at the loaf from above. Now imagine that you reached down and grabbed a single slice, and you took it out and looked at it. It would be a square. The bottom of a single slice is the length of the base that we found back in step 1. Now the area of a single slice, since this is a square, will be the base squared. We already have an expression for the base, so to transform this into an expression for area, we just need to take the length of the base and square it. And that's the end of step 2. The last step is to find the volume of the solid. We can find the volume of the solid by adding all of the slices between 0 and 1. Integration is addition. So we can add up all of the slices by integrating the area between 0 and 1. Since we already had an expression for area, all we have to do is integrate from 0 to 1. This problem is calculator active. So let's type this expression into the calculator. We are integrating from 0 to 1. So we will start by hitting Math 9 and 0 to 1. Next we are squaring all of this. So we are going to need a parenthesis other than the one that you already see. So there it is. Next we need the square root of x. And we are doing minus x squared. And now we close the parentheses and square that. Finish it off with a dx, and that's it. 0.129. And the answer is A.